Are you looking for a way to take your IAC to the next level? Terramate might be able to help you out. What's up, everybody? This is Ned Bellavance, nedinthecloud.com, and welcome to a sponsored episode of Terraform Tuesdays. This week is part one of a two-part series investigating what Terramate is and how it can help transform the way you write, run, and maintain your infrastructure as code. This week, we'll be focused on the Terramate CLI for code generation and orchestration. In the next video, we'll get into Terramate's cloud platform and how the two integrate together to give you better visibility, vulnerability detection, and faster running pipelines. But before all that, what is Terramate, and how do you get started with it, and what issues is it trying to address? I've said in a few prior videos, check out my Terraform Stacks one for a little more context, but what I've said is that giant IAC configurations have become somewhat of an anti-pattern. In the same way that a monolithic application can be difficult to update and maintain, having a giant Terralith can present the same kinds of problems. For instance, every time you run a plan, it has to refresh every object, which means that your plan process starts getting a little bit long. Also, the changes that you make in your code have to be orchestrated across every group that's using that Terralith. So that could be your network team, your security team, and the applications team, just to name a few. In the same regard, permissions management becomes a nightmare across all of those teams because they all need access to this single code base. Also, all the resources in your configuration have to be using the same versions of the providers, which means when you want to upgrade to a newer version of the provider, there's a lot more to test across multiple teams. And finally, partial deployments are sometimes required when you have unknown values that are required by something else in the configuration, especially if it's a provider configuration. There are some really nice things about having a massive root module, though, and it's stuff like all your code is in the same place, so it's pretty easy to parse and understand what's happening in the code. Also, your backend and provider versions are all defined in a single place. It's all using the same state backend. And like I said earlier, all the provider versions are defined and they're available in a single file. Also, referencing resource dependencies is super simple. You just reference another resource or data source in your config, and Terraform includes that in its graph. And also, previewing changes for an environment all happens in a single place. You don't have to do multiple runs across multiple configurations to see what's going to happen. In an ideal world, it would be nice to have a tool that could break up your Terralith to avoid the pitfalls of massive root modules while still maintaining some of their benefits. That's what Terramate is aiming to do. And they don't just do it for Terraform. They also do it for OpenTofu, Terragrunt, Helm, Pulumi, and Kubernetes. Terramate is composed of two components. We have an open source CLI that is free to use, and a cloud platform that integrates with the CLI to provide additional insight and visibility into your managed infrastructure. We're going to be focusing on the cloud component in the next video, so I'll put that to the side for now. Instead, let's talk a bit more about what the CLI can do. At its core, the Terramate CLI is a wrapper around other infrastructure as code tools. It automates and orchestrates the deployment of multiple infrastructure as code components. These components are referred to as stacks, and Terramate allows you to run commands against your stacks in parallel. You can even define specific scripted actions to run, so you don't have to type the same series of commands every time. Terramate also supports dynamic code generation, so you can have it create HCL or other generic files for use by your stacks. You can use the generation feature to cut down on repetition in your code and remove the need to update the same value in every stack that you're managing. As I mentioned, although the name Terramate implies that it only works with Terraform, that's not the case. Terramate can also orchestrate runs with OpenTofu, Terragrunt, Pulumi, ARM templates, and CloudFormation, just to name a few. We'll be using Terraform in the demonstrations. This is Terraform Tuesday after all, but just bear in mind you could apply the same principles to your IAC of choice or even combine them. Speaking of a demo, why don't we jump into an example deployment and see how we can integrate Terramate to break up our root module. All right, over in Visual Studio Code, I have a repository here that's called Globomantic's Web Stack, and the original configuration is in the original directory. So let's open that up and see what we're working with here. This is our original root module. Inside of the main.tf for the root module, it defines the Azure RM provider, so this is using Azure to deploy, and then it has a series of modules. There are 3 modules involved here, one for the network, one for a virtual machine, and one for a database. Each of these modules can be a stack in their own right, so part of what we want to do with Terramate is to create each of these modules as a stack and then wire the various modules together, thereby breaking up our Terralith. A few other things to note about this configuration. If you look at the settings for the module, it has a lot of variable values in common. The prefix, the suffix, the location, and tags are all inputs that are shared across all 3 modules. And then there's some module-specific settings, like the CIDR range and the subnets for the network module. Currently, those values are coming from a Terraform.tf vars that has all of the values that we need, both the common values and the ones that are specific to the modules. In terms of the backend definition, I have a backend config.hcl file that has my backend configuration that uses an Azure storage account. I want to continue to use this same backend when I break these modules into stacks, and each of those stacks will have its own instance of state data. Last thing to note is in the Terraform.tf, we're using version 3 of the Azure RM provider, but I want to make it relatively easy to upgrade from version 3 to version 4 when I'm ready for each stack. The last thing I want to point out is that the virtual machine module makes use of a module output from the network module. Specifically, the VM subnet ID is set to subnet 1 of the subnets that are created by the network module, and I need to maintain that across the deployment when I break these up into stacks. How does Terramate organize things, create stacks, and generate these other files? It makes use of files ending in .tm.hcl, so it does use HCL to define the stack information and other settings about the configuration. You can make use of these tm.hcl files in a folder hierarchy to define global values, configure state backends, and generate regular files and HCL files. So rather than explain more about it here, let's get started by creating our own stacks from the original configuration that has the single root module. Before I make any changes to the files in the original directory, I'm going to create a new folder called Transform so we don't mess with the original. And I'm going to copy the module directories from the original directory over to the Transform directory. I'm not going to copy any of the root module files since we'll be replacing their functionality with Terramate. Now we have to create our stacks. If we already had root modules for each of these modules, we could simply run terramate create --all -terraform. But since our modules don't have those root module components, I'll instead run terramate create for each path. After I run terramate create network, if we look in the network directory, there is now a stack.tm.hcl file in the network directory, and it's generated a unique ID for this stack. I'll repeat the same process for the database and then for the VM directory. Terramate supports putting your stacks in a folder hierarchy to indicate dependencies and precedents. Subfolders have dependencies on parent folders. Or you can use before and after statements in your stack definition, which is the preferred way now. Stacks also can have tags applied to them for filtering purposes. And this is a pretty powerful idea. I'll give the network stack the tags network, Azure, and Azure RM backend so that we know it's for the network using the Azure provider and using the Azure RM backend. For the VM, I'll add compute, Azure, and Azure RM backend tags. And lastly, for the database, I'll add the database Azure and Azure RM backend tags. Now we know that the VM stack needs a subnet ID from the network stack, which means that the network stack needs to be deployed first. Now let's also say that the database needs the network setup as well, although there's not a direct dependency. To the VM stack, I'll add an after argument and add an entry to the list for tag network. This tells Terramate that it needs to deploy any stacks tagged as network before deploying the VM stack. I'll do the same for the database stack as well. Cool. Now that we've added some order to our stacks, what else do we need? Each of our stacks is going to need provider information, like the version of the Azure RM provider to use and a provider block for Azure. We can set that in the root folder by creating a providers.tm.hcl file and adding some settings. I'll start by adding globals. Globals are a way to create values you can reference in other Terramate files. That includes Terramate files in subfolders as well. So they're kind of like Terraform locals, but inherited by other subfolders, which makes them global. So I'm going to add some globals here for the Azure version and the source I want to use for the provider. To write these values to a file, I can add another block here called generate HCL, and the name label is the name of the file to create. Inside the block is the contents of the file, which I'll use to create a Terraform block, and inside of there, a required providers block. This file will be created in each stack by default. You can control this with either a stack filter argument or a condition argument. For instance, I could say that this only gets created when the stack has the tag Azure, but I'll leave that as an exercise for you if you're interested. The other file we need is a provider.tf file, which I'll create in the same way. This time, we're just adding a provider block for Azure RM with the empty features block inside of it. Now, if we want to upgrade our version of Azure for the stacks or add something to the provider block, we can do that in a single place. How do these files get created? By running Terramate generate. So let's do that now. First, I'll run Terramate FMT, which will properly format all my tm.hcl files. Then I'll run Terramate generate, and it will create 2 files for each stack. Terramate manages the content of these files, so if I need to change something, I can update the generate HCL block or the globals, and then run Terramate generate again to modify the existing files. Now, what else do we need here? Well, I'm using the Azure RM backend, so I need a backend file for each stack. I'll create a new Terramate file called backend.tm.hcl in the transform directory, and again, we need to establish some global values here. My stacks are all using the same storage account, resource group, and container for state storage, so I need globals for each of those. I can copy my existing settings from the original config, but the key needs to be unique for each stack. No problem. We'll take care of that when we generate the HCL. I'll start with a new generate HCL block, and Copilot might give me a helping hand here. Boom, there we go. Thanks, Copilot. It got the resource group name right, and we can continue by adding the storage account name, the container name, and now instead of the key, I'm going to set the use Azure AD auth, and that's all the settings we're getting from our globals. Now to craft the key, what I can use is a special expression called terramate.stack, and that has multiple properties, including the stack ID and the stack name. So what I'll do is use the stack ID.thestackname.tfstate to generate a unique key for each stack that we're working with. When the code generation process runs, it happens from the context of the stack. So any expressions I put in that refer to the stack ID and stack name will get rendered to the current stack's name and ID. Before we generate the backend file, is there anything else common to all the stacks that we should set? What about input variables? Yeah, the stacks have a bunch of input variables that are common amongst them: the prefix, the suffix, location, and tags. So what I'll do is create another file for defining variables and add some globals to it for each of those settings. I can copy the values from my existing terraform.tf vars and then update a few values to reflect that this is now being created via Terramate as opposed to the original solution. Once I have those values ready, I'll create a file called global.auto.tf vars so I can still set other settings locally on each stack. Now I'll run Terramate fmt and generate again to create these files. Looking in the network directory, we now have a backend.tf file that has our backend configuration and a unique key that's specific to the network stack. And we have our global.auto.tf vars file that will be automatically found by Terraform when it runs. Cool, we're making progress. Now to configure values for each stack. I could simply create a terraform.tf vars file for each stack, but why not let Terramate handle that for me? In the stack file for the network stack, I'll add a global section here with settings for the network. If I define a global with the same name as one defined higher up in the hierarchy, this one will take precedence, so I could override the location or the tag setting here. There's also a way to merge settings together, but that's a slightly more advanced use case. Once again, I'll copy the values from the original terraform.tf vars, and this time I'll generate an HCL file that's called stack.auto.tf vars that contains these additional settings. Terraform will merge the contents of the global and the stack.tf vars files together. I can rinse and repeat for the VM stack, which only has two variables that are not covered by the ones we're defining at the top level, and for the database stack, I don't have to add anything since there are no variable values aside from the ones that we've already set at the top level. Now there's one more thing we need to deal with before we deploy our infrastructure, and that's the VM subnet ID for the VM stack. In the original configuration, we could simply pass the subnet ID from the network module to the VM module. It was all part of the same root module, so Terraform handles internally the fact that the value is unknown during plan. Now that we're splitting things up, the VM subnet ID is an input variable for our VM stack, and all input variables have to have a value when you run plan. There's two ways of dealing with this. You could create a data source in the VM stack that accesses the remote state data of the network stack and gets the subnet output values. In order for this to work, the network stack has to be completely deployed before the VM stack can be planned. Otherwise, there'd be no value in the state. When orchestrating this deployment, we'd have to defer planning of the VM stack until the network stack is fully deployed. The other option is to use an experimental feature in Terramate that allows you to share outputs across stacks. It's called shared outputs. The process is to create a sharing backend block at the top level, and then define shared outputs on the source and inputs on the target. You can also supply mock data for Terramate to use when the value isn't known yet. This gets around the need to fully deploy the network stack before planning the VM stack. Let's give shared outputs a try. At the top level, I'll create a shared backend.tm.hcl file and add to it a sharing backend block called Terraform. Inside the block, I have to specify the backend type. Terraform is the only currently supported type. Also a command to run, which essentially runs terraform output.json, and the name of the file to create with these settings. At the network stack level, I'll add an output block to the stack config called VM subnet ID with the backend set to Terraform and the value set to the Azure RM subnet.main and pick subnet 1 and the ID of that subnet. Lastly, at the VM stack level, I'll add an input block to the stack config called VM subnet ID. This block needs to know which backend type we're using, the value to get from that backend, which stack has the output, and optionally mock data to use if there is no value available yet. For the stack ID, I can simply copy the network stack ID. The mock data does need to be a valid subnet ID format, but it doesn't have to be an actual existing subnet. Lastly, we already have an input called VM subnet ID in the variables.tf file for the VM module. So I'm going to comment that out so there's no input variable naming conflict. Before we deploy anything, I'll run Terramate FMT and generate one more time to create the files for our stack.auto.tf vars and the shared outputs. In the sharing file for the network stack, it created a new Terraform output called VM subnet ID. And for the same file in the VM stack, it created an input variable called VM subnet ID. Now, how does this actually work? Let's start with some basics around the CLI. We're going to be using the command terramate run to kick off a Terraform plan. Terramate is a wrapper around your IAC tool of choice, so we're going to provide it with some information about which stacks we want to run and any options about those stacks. Then we will tell Terramate what command it should run for each of those stacks. What is the first thing we need to do for any Terraform configurations? We need to initialize the root modules. That's exactly what we'll do here. And we can do it for all of our stacks at once by running terramate run -- terraform init. Anything after that double dash is the command to run against each stack we've selected. I'm running the command from the transform directory, so it's going to apply to all the stacks defined in the subfolders. And we immediately get an error. What's that all about? Repository has uncommitted files. This is actually a feature of Terramate, which I'll explain in more detail in a moment. For now, let's just commit our changes to the repository. Looking at the execution of the stacks, it starts with the network stack because the database and VM stacks say to run after the stacks tagged with network. Then it does the database stack, and then finally the VM stack. By default, Terramate doesn't run the stacks in parallel, but we'll change that when we run Terraform plan. After the initialization, I have some new untracked files in my repository. Those would be the Terraform lock files for each stack. I'll commit those real quick. And now we can run plan. I'll run terramate run with -j to indicate parallel execution, which I'll set as 2. And then we'll add Terraform plan to the end. I don't expect this to finish without input from me. It'll start by running the network stack again, and when it gets to the VM stack, it's going to run into an issue. It's going to prompt me for input for the VM subnet ID. Now, didn't we tell it to set that with the shared outputs? Well, we did, but we need to tell Terramate to set up those outputs with some flags. I'll cancel out of here and rerun the command, but this time I'll include 2 additional flags. -- enable sharing and -- mock on fail. The first flag processes the sharing backend, and the second one will use our mock data if no matching output is found. What Terramate is doing in the background is running Terraform output-JSON after the network stack plan completes, and then it takes any outputs we've defined and creates environment variables called tf-var input name for any that we're using as inputs for another stack. When the Terraform plan for the VM stack runs, the input variable VM subnet ID will find a value through that environment variable. The mock on fail flag simply uses our mock value if no output value is available. Okay, the plan's all completed successfully, and we could review them to make sure that they're actually deploying what we want. You may have also noticed that the database and the VM plans ran concurrently, and that's pretty convenient, especially if we had a lot of stacks we were trying to plan at the same time. Now let's actually deploy our environment. I'll run the same command as before, but this time I'll change the command to apply with the auto-approve flag so we don't have to wait and get prompted. I'll jump ahead to when the deployment has finished. And it's done. We've got our whole stack deployed. Now, what about changes? You might be wondering about that error we got when we had untracked files and Terramate wouldn't run the run command. Now it's time to get back to that. Terramate is integrated with Git to track changes. If you change something about your code and commit it to the current branch, Terramate uses the Git diff to determine what has changed and thus which stacks need to be updated. And so it really wants you to commit your code before running any commands. Let's see this in action. I want to change the VM size used by the VM module. I'm going to update the value to B2S and run a Terramate generate to update my stacks.tfvars file. Now I'll commit the changes to Git. Now to apply these changes, I could target just the VM stack by using the tags associated with that stack. I could do Terramate run -- tags and then compute, and that will apply only to the VM stack because that has the compute tags. But there is another way. If I run the command Terramate list, it will list out the stacks. But if I add the -- changed option, it will only show me the stacks that have changes, and it gets that from Git. I can use the same changed flag with the run command and use my previous run command to apply the changes only to the VM stack. When I kick off this run, it goes directly into the VM stack and starts applying those changes, skipping the network and database stack since they don't have any changes. This is a huge time saver if you've got a lot of stacks. Each Terraform plan takes up time, and even though we're running things in parallel, it still takes time to run a plan against stacks that don't have any changes. Soren from Terramate showed me a repository where they're managing over 100 stacks, and this was a game changer for them. Once this gets added into a CI/CD pipeline with pull request-based plans, you can see how the changed flag can significantly cut down on planning runs and get PRs through faster. In fact, we'll be covering exactly that in the next video where I dive into Terramate Cloud and CI/CD integration. The Terramate CLI is a wrapper around existing IAC tooling, allowing you to define hierarchies and abstractions through code generation and graph creation. It's similar to something like Terraform Stacks, TerraGrunt, or many other solutions trying to crack this Terralith problem. There's a few things I really like about Terramate. Although you're adding stack files and higher level configuration, the code generation process creates regular old Terraform files. You're not locked into using Terramate forever. I can still dip into one of the stack folders and run Terraform directly if I want to. Terramate supports both Terraform and OpenTofu. So if I want to switch over to OpenTofu, I don't have to worry about compatibility. And in fact, it makes the cutover easier by making it simple to update provider sources to the OpenTofu registry. Terramate uses Git integration to track changes. Now, this can save you a lot of time when kicking off plans. It only runs in the stacks where it actually needs to. The Terramate configuration files all use HCL and Terraform-friendly syntax, so I'm not learning a whole new configuration language when I'm trying to build out the stacks. Lastly, the Terramate folks are super responsive to problems and feedback. I ran into a roadblock or two while trying to build my demo, and rather than telling me to just read the freaking manual, the Terramate team gently showed me where I had gone wrong. Ultimately, you are adding some level of complexity to your current Terraform root modules. You could try and do this through automation pipelines and custom scripts, but those don't really understand infrastructure as code, so it's always going to feel like a kludge and a little difficult to maintain. Terramate provides an alternative that is declarative in nature and uses HCL. Is it worth the effort? As always, that depends. But in the next Terramate video, we're going to take a look at Terramate Cloud and its CI/CD integration, and I think that might tip the scales a bit in Terramate's favor. That's going to do it for today's video. First off, a big thank you to Terramate for sponsoring this video. While they did provide a little direction, the opinions and thoughts expressed here are mine and mine alone. I also want to thank you, the viewer, for watching. You are an excellent human, and I hope you've learned something useful that will help you in your day-to-day responsibilities. I'd also love to hear your feedback on Terramate. If you head over to terramate.io, you can take it for a test drive, and you can even clone the repository I've been using for the demo. Let me know what you think in the comments down below or on LinkedIn. Thanks again, and until next time, keep calm and terraform on.